Hello and welcome back to my YouTube channel. Today we will be learning about Gram-Schmidt process. Gram-Schmidt process, as the name suggests, was invented by two persons, Jordan Peterson Gram and Erhard Schmidt. To understand this process, we need some basic understanding of orthonormal basis and the inner product space. Applications of Gram-Schmidt include QR decompositions and Lie group decompositions. The algorithms used are vector projections and orthogonalization. First, we select the vectors, initial set of independent vectors. Then we project the vectors on the subspace. By removing these projections, we get orthogonal vectors. Then we normalize those vectors to get the orthonormal vectors. So, starting with a linear set of independent vectors, we end up getting an orthonormal set. First, let's try to understand what do we mean by vector space. So, let's say we have two vectors v1 and v2. So, now I want to add v1 plus v2. So, using the parallelogram method, I create a parallelogram with v1 and v2 as its side, and the diagonal gives me the resultant vector. Similarly, if instead of v1, I take minus v1 by 2, then I get a vector that is along the y-axis. And following the same process, if we can take any linear combination of v1 and v2, we can end up getting any vector in this 2D subspace. So, we can say v1 and v2 are two linearly independent vectors that span the 2D vector space. That is, any 2D vector can be represented as a linear sum of v1 and v2. Now let's understand the concept of dot product. Let's say we have two vectors a and b, where b is along the x-axis and a rotates with an angle theta having the same length as b. So now the dot product, the formula says mod of a times mod of b times cos theta. So now the resultant will be 25 times cos theta. And as we increase theta from 0 degree to 90 degrees in a step of 10 or 20, then we see that this projection length, the red vector, the length of the red vector reduces. So it says that vectors a and b, if they are aligned along each other, their dot product will be higher, while when they are perpendicular, the dot product will end up being 0. So this was the basic idea used behind having a projection and then using that projection to make orthogonal vectors. Now let's understand Gram-Schmidt process with a 2D example. So again, we take two vectors v1 and v2. Now, first I calculate the dot product between v1 and v2 divided by the dot product of v1 with itself and project it along v1. So this is the projection of v2 along v1. We call it a. Now, if I subtract this a from the v2, I get this dotted red line, which I'll shift to the origin and call it b. Now, if I add a and b, the resultant will be v2, and interestingly here, b is perpendicular to a, or b is perpendicular to v1. Now, the final step of Gram-Schmidt process is to scale those vectors a and b so that they become of unit length. Now let's visualize this process in 3D environment. So let's say we have three vectors v1, v2, v3, which are inclined towards each other at some angle which is other than 90 degrees. So now, for the first vector u1, we will take v1 as it is. And then, if it is not normalized, we'll normalize it. But in this case, it is already done. Now, for the second vector, when we are taking v2, then we'll take its projection along u1, subtract this projection from v1 to get a perpendicular vector to u1. You can see now u2 is perpendicular to u1. Now, since it is not normalized, we'll normalize it to get e2. Similarly, for v3, we'll take its projection along u1 and u2, subtract those projections to get a vector that is perpendicular to both u1 and u2. Then again we normalize it to get e3. In this way, starting from three vectors v1, v2, v3, we get a final orthonormal basis e1, e2 and e3, which indeed forms a basis for R3, that is the three-dimensional vector space. Any vector now can be represented as a sum of these three orthonormal vectors. To perform it using numerics, this is the algorithm used. But this is susceptible to numerical instability. So another method, which is modified Gram-Schmidt, was proposed. In modified Gram-Schmidt, instead of taking the projection from all the previous vectors, it is taking projections from already created perpendicular vectors. So this adds up to the numerical stability of the method. Now let's take a look at the code of Gram-Schmidt. So we start off with the array n, k. Then we first normalize the first vector, and then for the subsequent vectors, we take the projections, subtract it, then finally normalize it. While in modified Gram-Schmidt, there is a if-else statement which says that if it is the first vector, we leave it as it is, but from the second vectors, we take the projections from the stored vector instead of the calculated vector. So this is slightly different with Gram-Schmidt, which adds on to its numerical stability. So now let's compare them side by side to see that there is just this block of if-else statement that is changed, else everything remains the same. Thank you for your time, and please download the course from my GitHub page and then start experimenting. In the next video, I'll be back with QR decomposition and its code. Also, please show your support by liking to this video and subscribing to the channel. It means a lot. Thank you.